Okay, so let's talk about the interconnection of these elements, okay? All right, so impedance and admittance of interconnected elements. If you were to take, so say we learned how to do resistors, capacitors, springs, dampers, fluid capacitors, thermal capacitors, all of that stuff last lecture. We did it all because we're talking generalized. We could do all of those things. No problem. Impedance, admittance, we have a table that tells us it and everything. We don't have to remember things. We've got it going on. So what happens if you put two of them in series, though? Should we just give up? If our system's more than one element, should we just walk away?
Yeah.
Just be over it? Yeah? I challenge you not to walk away, to instead review these notes. Because it's very easy to combine the impedances and admittances of individual elements. The first way that they can be connected is in series. And I'm actually going to define what I mean by series by saying that they share the same through variable. If they share the same through variable, they are in series. Okay? All right. So these are in series because they share the same through variable. N impedances connected in series have the equivalent impedance Z of S equals, and I want you guys to tell me what it is. Yeah, it's just the sum. So I'm going to use summation notation because I want to be fancy. But it's just the sum of all of the z's. Just add them up. And the admittance is, you may or may not have thought this was the case, 1 divided by the sum of, so from I equals 1 to big N, of so the 1 over y i's. Well, that's a weird y. I don't like that. I'm going to go back. There we go. That's better. So that it reminds us a lot of talking about electrical impedance and admittance as well. So which one's easier to compute? This one, right? Yeah, better. Parallel connections. So if elements share the same across variable, we say they're in parallel. So these ones are in parallel. So n impedances connected in parallel, like this, sharing the same across variable, have the equivalent impedance. So I'm going to write Z of S equals, and then I want you guys to tell me the next thing to write. 1 divided by sum from I equals what? 1 to N. Yeah. Nailed it. So this looks a lot like what we would do when we combined resistors in parallel, right? 1 over R1 plus 1 over R2 plus 1 over R blah, 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 blah. That's this formula. Okay. And the admittance is, there's a nice symmetry to all this. So can you guys guess what this is going to be? Yeah. It's good to see the symmetry. Okay. So let's do an example, shall we? For the circuit shown, what is the equivalent impedance? Oh my God, I'm going all the way to first example I do, and I give you 4 elements connected together. How hard am I, Professor? It's ridiculous. Okay. So, I'm going to give you guys a minute. I think you guys can do this all on your own. You're welcome. if you guys can prove to me you can do this, then maybe I'll show you guys the cool demo on Friday. No, I can't do it yet. We'll talk about controls, and then it'll be a lot more topical. I'll wait till the end of the semester. Okay. What? Oh, you guys aren't done? Okay. I'll come around and check on you guys. Yeah. You can combine them into one, simplify them into one term. I'm not going to force you to do it. I mean, if you want this example to be more than one line, though, you kind of got to simplify or something. Feels like you got to get your money's worth out of the example. We thought it looked so hard. So what is it? What is the equivalent impedance? So what was the first term? So I'm not gonna write something equal. I want to define a term. So what is the first part? R1 plus, and then so the impedance, we could just write like ZR1, ZC, ZL, ZR2. Do you guys want to do that, or do you guys want to plug it right in? Plug it right in. Okay, R1 is the impedance of this, plus the impedance of C, which is what? 1 over CS plus, so I'm just gonna do a big fraction. So it's 1 over 1/LS plus 1 over R2. Very good. That is the equivalent impedance. So if we were to simplify this down, I'm not even going to. I mean, we could do this. We could build this up one thing at a time. But writing this down, we can write down the answer and then simplify algebraically, which is pretty cool. Yeah, so there's really not a lot to it. We would want to find a common denominator and simplify this, but it's just algebra. It's not that bad. Okay. Got like the Nick Cage going on right now. I love it. It's awesome. I love it. It's cool. I wish I could do the Nick Cage. Nick Cage is like the most intense guy ever. Yeah, it is. I was worried about it. Yeah. The Statue of Liberty as well. You steal that too. I don't know. If you were that one magician, maybe you could do it. I think we could do another lecture in 6 minutes.